Hi everyone. Today we're going to talk about file systems, and starting off, what is a file system? Simply put, this is a layer of the OS that makes it easy for the user to interact with files and data. In other words, a layer of the OS that transforms the block interface of disk into files and directories. So a file is just a named collection of bytes of data, and a file is going to be composed of some metadata like its owner and permission bits, as well as the actual data or contents of the file. Now, how can we actually translate a physical file path into a location on disk? Let's first go back to what we learned about file systems in Project 1, or rather, just files. So, for operations such as reading or writing to a file, our system relies on a per process open file table. And each process has its own table, and the file descriptor provided by a syscall like read or write points to an entry in this per process table called the FTT. Now, that file descriptor entry, the entry in the FTT, points to a file description in a system-wide open file table, which typically keeps track of the inode. And multiple processes that access the same file are ultimately going to use the same system-wide entry. Now, what is an inode? I just threw that term around. We'll see the structure of inodes in a specific file system later on, but for now, an inode is basically some structure that contains important core metadata about files that allows us to find the file data on disk and uniquely identify that file. Some file systems do not use inodes, and we'll discuss those later, but a lot of Unix-like systems use inodes. So again, each file is uniquely identified by an inode, and an inode typically maintains a reference count to track how many open references there are to that file. When there are no more references, or when the last reference is being taken away, then the inode's contents can finally be deleted. And so, moving on to directories. What is a directory? You definitely have some intuitive understanding of this. But a directory is really a special type of file that contains mappings that map file names to file numbers. And file numbers are going to uniquely identify files, and we'll talk about what they represent in different file systems later on. And so on Unix-based systems, you can make two different types of links. Hard links are directory entries that map a file name to a file number. And soft links map a file name to another file name. So a normal directory entry is essentially a hard link where you have a file name and a file number, whereas with a soft link, that entry is a file name and a destination file name. So the OS is going to look up the destination file each time the program accesses the target file. And these are more convenient for producing trees of file names that are part of build packages, for example. You can also create symbolic links or soft links to files that are not actually on your file system. So you could create a soft link mapping a file name to another file that's actually in a different file system or like partition. And in certain file systems, you can create multiple hard links to the same underlying file, given that the file number corresponds to, for example, an inode that's reference counted. So if you have two different hard links to a file, when one hard link gets deleted, the file still exists until the other hard link gets deleted. If you cannot reference count the file, then hard links become infeasible due to what I just specified. So it becomes difficult if you had multiple hard links and you didn't know how many open references there were to a file to know when to actually delete the file's contents. And so we'll see that in a specific file system later on. Okay, and so to go into the main file system that we'll be discussing, FFS, or the fast file system, this is actually a Berkeley innovation and was released in 1983 as part of the BSD Unix OS variant. And BSD stands for Berkeley Software Distribution. And so in FFS, we reintroduce this concept of an inode, which is essentially a chunk of data that contains the metadata of a file, as well as pointers to the actual data blocks of that file. So the metadata here corresponds to the top of the inode and contains things like what user created it, typical read-write permissions, etc. So in the system-wide file table that we discussed earlier, each entry would point to an inode, and opening a file multiple times may result in multiple file descriptor entries that point to the same inode ultimately. And so the inode array contains inode themselves, and the file number corresponding to a given file gives us an index into the inode array. And so the file number is often also called the inumber, as in the index in the inode array. And this inode array is stored in a contiguous region on disk. So if an inode is smaller than a full disk block, we can pack many inodes into a single disk block. In Pintos, your inode structure is going to correspond directly to a full disk block, and you'll see that later on or in the Pintos file growth video. And so within each inode, we use a tree structure of pointers to the data blocks that we need for a file. And so a pointer in this context simply refers to a block number that corresponds to a specific block on disk. And the disk controller knows the physical location of the block corresponding to that number. So a direct pointer corresponds to a block number that maps to a block containing data of the file itself. And each inode is a fixed size, so we have a limit of how many pointers we can store in the inode itself. That leads us to the concept of an indirect pointer, which points to a block that is entirely filled of direct pointers, instead of pointing to a block of pure data for the file. A doubly indirect pointer is very similar, except there's two levels of indirection, so two levels of pointer-filled blocks, and the doubly indirect block is filled with pointers. Each pointer here points to an indirect block, which is also filled with pointers. So you can see this tree-like structure in the diagram on the right. And so when we're reading data from an indirect pointer, we first have to read the indirect block from disk, after which we can use the pointers inside of that indirect block to find the actual data block corresponding to that pointer for the file. So this means that compared to direct pointers, we have one additional disk access to find the data in a file associated with an indirect pointer. And this is fairly similar to the concept of a multi-level page table, if you remember that from midterm 2 content. So why wouldn't we just have a bunch of direct pointers in the inode instead, if we're saying that indirect pointers and thus doubly indirect and triply indirect pointers have more disk accesses associated with them? What is the actual benefit of having an indirect pointer? And well, if we had a ton of direct pointers instead, this means we would also have to make our inode a lot bigger, and we don't want to make inodes that big. In fact, at the very most, an inode should typically be at most the size of a block. And you can imagine if we could only store 200 pointers in a block, and we were only using direct pointers, then our file size is limited to 200 disk blocks. If instead, say, we replaced one of those direct pointers with an indirect pointer, our file size would increase by around 200 data blocks. Okay, so now we see the benefit of an indirect pointer. Without increasing the inode too much, we're able to still map that inode to a lot more data blocks for that file and thus increase the maximum file size that our file system can support. And so now you're probably asking, why don't we just use all indirect pointers? And well, most files in a file system are actually fairly small. This means that our file system should probably prioritize a simple design for small files, while still providing an easy mechanism to grow our files. So when we create and write to a file, the data is first written using direct pointers in this file scheme with this inode. And as the file grows, if we need to, we can use the indirect pointer or the doubly indirect pointer and so on. But we don't want to incur the cost of these extra disk accesses from reading indirect or doubly indirect pointers for smaller files if we don't have to. So that's why we start off with a bunch of direct pointers to easily accommodate small files, and then we have an indirect, doubly indirect, and possibly triply indirect pointer to allow our file system to have a few much larger files as well. Okay, so looking back at the bigger picture in FFS from a corresponding file path, we can determine that file path's file number, or inumber, which indexes into the inode array, tells us the inode associated with that file, and from there we can easily access the file's data. And so a few more things. As I previously mentioned, the metadata for a file is stored in the inode itself, as opposed to file systems like FAT, where the metadata for a file is stored in the directory entry. And in terms of free space management, as you probably learned in lecture, an optimization from a later version of FFS, that is now the more currently used version, is that sorry, my computer was glitching. An optimization for how we store or keep track of blocks that are free is that FFS uses a bitmap where we use essentially a fixed size array where each entry in the array is just a bit that corresponds to a specific block and indicates whether or not the block is free. And initially, the BSD 4.1 version of FFS used a list or a linked list of free blocks, and this was later changed to a bitmap. Okay,